Good day, ladies and gentlemen personalities. Today we are dealing with mathematics paper 2, the topic called Euclidean geometry. So what is Euclidean geometry? Euclidean geometry is just a fancy word for a geometry of a circle. So whenever you are speaking about Euclidean geometry, you must know that there is what? There is a circle that is involved there. Right, now this topic is examinable at grade 11 syllabus caps in South Africa, and then also in grade 12. So if you are doing grade 11 or you are doing grade 12, then make sure that you sit still and you listen if you are doing pure math, because this is going to help you tremendously. All right, so what we are going to do is few things. So number one, we are going to introduce few terminology that are used in geometry, in Euclidean geometry, and then we are going to explain those terms, and then we are going to illustrate those terms as well. So that is number one. So number two, we are going to introduce the first theorem, and if time agrees, we are also going to prove the first theorem. Right, so we have already mentioned that when we are talking about Euclidean geometry, we are talking about the geometry of a circle. So you will have a circle which is something like this, right? This is a circle. Okay, so when you have a circle, if you can have a point in the middle, there is this point. Now the point that is in the middle is called the center. The center point. Okay, that is the center of what? Of a circle. Right, now if you have a center of a circle, now what you can do is you can actually, before we even get there, there is a center, and then these places, these linings of a circle, we call them, you can call them either circle. Okay, so if you've got a line from here to here, you can say it goes from a circle to a circle. That is acceptable terminology in this topic. And then, but you can also call it a circumference. Okay, you can call it a circumference. So when you are saying a circumference, you can say that referring to any of these parts of the circle. All right. All right. So let's continue. So if you have a circle like this, you can be able to draw a line from where? From the center of a circle, and then that line goes to the circle. Okay, so a line from a center to a circle to the circle, there is a name for it, and that line is called radius. Radius. Okay, and then we denoted it by what? By r. Okay, it is a radius. So if you can have a line from the center of a circle to any part of the circle, then that line is called what? Is called the radius. Does that make sense? Okay, now young people, it is very important to note that it does not matter where this line is. As long as this line moves from a center of a circle into a circle, it is still radius. So what do I mean by that? I mean, if you can have another line from a center of a circle to the radius, can you see? It is another line. Now this line is also called what? Is also called a radius. Okay, it is also called, it is called a radius. Now if you've got two radiuses, if there is such thing, because it looks like you can have such thing in English, in mathematics you then call these two things radii. Radii. So when you've got two radius, so the plural of radius is is radii. So it's radii. Can you see that? This is the plural of what? Of radius. So one radius, and then when there are two, we then refer to them as what? We then refer to them as radii. Okay, wonderful. So if you can have another line from the center of a circle into a circle, that is still a radius. As I said earlier, it does not matter where it goes from, as long as it comes from a center of a circle to the circle, then we refer to it as what? As a radius. All right. Now, say for argument's sake, you decide to extend this line. So you've got a line from a circle to another circle, passing through what? Passing through the center. Now you've got a name for that line. What do you call that line? You call it a diameter. You call it a diameter. So you denote it with what? You denote it with D, or some people denote it with a capital D. It doesn't really matter. All right. What is important is that if you've got a line from the circle to the circle, to the other side of the circle, passing through the center, then we refer to that line as what? We refer to it as the diameter. All right. Wonderful. So I think by now you can actually see something, that there is a sort of a relationship that exists between a diameter and the radius. But before we can say that, guys, I just want to emphasize one thing. I'm sure some of you know it, but I just want to emphasize it for a record. Ladies and gentlemen, personalities, if you have a circle, each and every radius that is there in one circle is equal to each other. It does not matter where it is. They all radii are equal. Okay, so what does that mean? That means the distance from here to here is equal to the distance from here to here, is also equal to the distance from here to here, is also equal to the distance from here to here. Okay, all radii are equal. Now that is very important. So what have we introduced? We've introduced a circle, we've introduced a diameter, we've introduced a radius and a radii. Okay, now right now, as you can already see, if we then say that all radii are equal, therefore whenever you have a diameter, then there is a relationship between a diameter and a radius. Now what is that relationship? Is that the diameter is made of two radius. Okay, so D, which is for diameter, is equal to what? Is equal to 2r. This is a very, very important relationship that you have between what? Between a diameter and a radius. Now, this relationship, how can it help you? It can help you because if you have a radius, then you can actually use that radius to find the value of a diameter. Or if you have a diameter, you can use that value of that diameter to find what? To find the radius using this relationship, the radius and the diameter. All right. Wonderful. Now, I want you to introduce you to something else. Something that we call this thing a tangent. Now, what is a tangent? When we are referring to a tangent, we are referring to a line that touches the circle exactly at one point and only at one point. Okay, please don't take note of my terrible handwriting. This should be a straight line. Okay, so this is a tangent. Tangent. What is a tangent? A tangent is a line that touches the circle only and only way at one point. Okay, if it touches it at 2 points, then it's no longer what? It's no longer a tangent. Now a tangent can be here, it can be here, it can be here, it can be here, it can be anywhere along the circle, as long as it is going to touch what? It is going to touch 1 point. Does that make sense? That is the terminology. All right. Now there is some other things, other terms that are also very important, and for these terms I'll have to write another circle so that I can be able to illustrate them very well. So let's say we've got a circle like this. All right, we've got a circle like this. Now if you can have a line from a circle to the circle, but that line doesn't pass through the center, then we can call that line a chord. It's a line, it comes from a circle to what? To a circle, and it doesn't pass. Let's say the center is here, it doesn't pass through the center. Okay, it just goes from a circle to a circle. So a line from a circle to a circle is called what? It's called a chord, and this is how you write it. Chord. Okay, what is a chord? Is a line from a circle to the circle, but it does not pass. That is a condition. Ladies and gentlemen, personalities, it's my, because once it passes through the circle, then it's no longer a chord. It's what? It's now a diameter. Right? So it's a chord. Now, when you have a circle, ladies and gentlemen, personalities, and then you introduce a chord inside the circle, then that chord will divide the circle into 2 parts. Now, what do we call that 2 parts? So you've got a chord, and then the chord will then give you 2 parts. Part 1, and then part 2. Now, what do we call that part? We call those parts. We don't call them parts mathematics. We are very special. We've got our own terms. We call them segments. Okay? So it's gonna be the first segment, and then the second what? Segment. Okay, so whenever you introduce what? Whenever you introduce a chord, you will then result, or as a result, you will have segments. Now there is a way in which we classify these segments. A chord will always have a bigger segment and a smaller segment. Okay, so now the bigger segment, like this one, this bigger segment is simply a part. It's just that in the context of Euclidean geometry we call it parts. So basically, so the biggest segment, we call it what? We call it a major segment, and then this one we call it a minor segment. Okay, which simply means a small segment. Minor, anyway, you can say minor. Whenever we're speaking about minor, we are speaking about something that is small. Right? Something that is small. So ladies and gentlemen, personalities, this is basically what we are referring to. Okay, but also if you are standing here in this segment, you can simply call this segment, you don't necessarily have to call it a major segment, though it is a major segment. You can call this one the other segment, and then if you are also standing here, you can call this one the other segment. Okay, because this is the segment that you are in, and then this one will be the other one. And then when you are standing here, this will be the segment that you are standing in, and this will be the other one. You will actually see these kinds of things when we speak about like the theorem called Tan-Chord theorem. But don't worry about that. We'll get to it when time agrees. All right. So, ladies and gentlemen, personalities, we are going to speak about theorems. And in theorems are going to say something about these parts or these terms that I've just mentioned. And then these terms, they relate to each other in a certain way. And then when they combine together, they form something else. And you will see those things, those combinations, those relationships that are there are going to be described in a form of theorems. All right, remember when I was speaking about geometry in general, there's something that I said about it. I said the theorems are things. So things, a tangent is a thing, a radius is a thing, a diameter is a thing. So you've got different things in geometry, and then those things are related to each other in a certain way. Now, the way in which they are related, or the way in which they relate to each other, is then referred to. When it's clearly described and it can be proved, we then refer to that as what? As a theorem. Okay? So, we are going to begin with the first very, very beautiful theorem of grade 11 Euclidean geometry. Okay, so what is that theorem? It's theorem 1. And then it says the following, and I quote. It says a line drawn from the center perpendicular to what? To the chord. That line, what does it do? It bisects the chord. Okay, so a line drawn from the center perpendicular to the chord bisects the chord. Okay, this is theorem 1. Theorem 1, a very important theorem, wonderful people, which is also examinable, which means you must know it, you must know the proof of that theorem as well. Okay, so in this theorem, it says that, okay, you've got a circle, and then you've got what? You've got a chord, and then you've got a center. Okay, so this theorem says the following. It says that if you have a line that is drawn from a center to the solid, let's call it center O, and let's call this PQ. Okay, so if you've got a line that is drawn from a center to the circle, but that line, if that line is perpendicular to the chord, then that line, what does it do? It then bisects the chord. Okay, so let me just find a different color so that I can be able to illustrate this properly. So what does bisect mean? Bisect simply means that it cuts into two equal parts. So that means that now if you've got R here, therefore it means this part is equal to this part. Okay, that's what bisect means. So it says that if you have a line that is drawn from a center and then that line is perpendicular to the chord, then that line bisects the chord. All right. Now, if you have used this theorem, ladies and gentlemen personalities, there is a shortage way in which you should show that you have used this theorem, which is basically a short version of this theorem. So what do you then say when you have used this theorem? So when you have used this theorem, you say the following. You just say, I'm going to write it with this, you say perpendicular from center bisects chord. Okay, so this is how you show that you have used this theorem. Remember, a theorem is a theorem because at some point in time it has to be used. Now let's pick one of the cases where this theorem could be used. All right, let's look at this problem. They are saying find PR. Can you see what is PR? PR is this from here to here. Okay, so what you have here, you've got a circle, you've got a line from a center of a circle to the chord, and then it's perpendicular to the chord. Okay, what you know is that PQ, so the distance from here to here is 24. Now they want you to find out what is the distance from here to here. All right, so how do you find that? Okay, ladies and gentlemen personalities, you can all see that in this kind of a problem you will use this theorem. Okay, so what is happening here? So you will then say here, okay, you've got this PQ which is equal to 24. Okay, you must reiterate. So PQ is equal to 24 centimeters. Why? We are given that. Okay, can you see that? We are given that PQ is equal to 24. Okay, but now our law, what does it say? It says that if you've got what? If you've got a line from a center of a circle to the chord, and then if that line is perpendicular to the chord, then it bisects the chord. Okay, so this is 24, which means that this part is going to be equal to this part. Okay, so that means PR is going to be equal to RQ. Why? Why? Because of the theorem that says perpendicular from center bisect chord. Okay, so can you see PR is equal to RQ? Can you see that? Now, since PR is equal to RQ, therefore it means that you can then say PQ is equal to what? Is equal to 2PR. Why? Because PR is equal to RQ anyway. Can you see that? Now PQ is what? PQ is 24. So you say 24 centimeter is equal to 2PR. Can you see? And then divided by 2, divided by 2, and then this 2 is going to cancel this 2, and then 24 divided by 2, that is 12 centimeter is equal to PR, which then says PR is equal to 12 centimeter. Okay. Ladies and gentlemen, personalities, if you did not know this law, even though you knew that PQ was equal to 24, but there was nothing that shows you how PR relates to RQ up until you had this first theorem that says that a line drawn from a center perpendicular to the chord bisects the chord. All right. So this is one of the case where this theorem works. Okay. Now, I just played around with this theorem like this just to show you how it works and how it relates. But basically, in real practice, you can, from here, you can go straight and say PR is equal to 12 centimeter, and then the reason will be what? Perpendicular from center from center bisects chord. Okay, you can easily say that, but allow this process to build itself up in you. Do not rush it through. Okay, wonderful. Let's look at the second one. Can you see? All right, now we want to find RQ. Okay, can you see that? Now we are given PR, which is equal to 8. Okay. Now, from our theorem again, we know that if we've got a line drawn from center parallel to what? To the chord, that line bisects the chord, which means whatever this is, then this is also 8. So you can go straight from here and say RQ is equal to 8 centimeter. What is the reason? It's because of this theorem. Now, what is the shortest version of this theorem? You say perpendicular from center bisect chord. Can you see that? And ladies and gentlemen, you are done. You get a mark here for the statement. You get a mark for the reason. All right, wonderful. Now, ladies and gentlemen, let us then do the last part of everything, an elephant in the room, and let us try to prove this theorem, because the proof of this theorem is actually examinable. That means in your exam you may find something that requires you to prove. You could be asked to prove this theorem. So when they ask you to prove the theorem, how do you then prove it? Okay, so it's a proof. Let's see. Okay, so but before you prove, guys, you must do a construction. Okay, now whenever you do a construction in geometry, you must actually tell the person that is reading that I've done a construction, and then this is the construction that I've done. Okay, so what is the construction that you have done here? Okay, so the construction that you have done here is, we have, so this is construction. You then join O, you join the center, you join the center O, and P to form what? To form OP. Okay, that means you do this. Can you see? You do this. Now you've got OP. Please make this a broken line, because it's not part of what you are given. You are creating it yourself. Okay, and then second, you will also join O with Q to get what? To get OQ. Okay, again, we draw some dotted line here. Aha. Can you see that? Now you've got a circle, you've got a triangle here, and then you've got a triangle here. Now I want you to look at this, and I want you to look at it rather very carefully. Okay, so remember you had a right angle here, right? It was given to you, right? So because it's 90, remember when you've got a straight line, therefore both of these things should give you what? Should give you 180 degrees. So if this is 90, then the other one is also what? The other one is also 90. Okay, so what you need to do, okay, so you've got two triangles. The first triangle that you've got triangle what? Triangle OPR, which is this one, OPR. So in triangle OPR, can you see that? You've got OPR. Now, when you name the second triangle, the second triangle, make sure that you name it in a way that will also align with the other one. Okay, so in triangle OPR and triangle what? Triangle OQ now, QR. So what is happening in triangle OQR? Okay, so first of all, you must note that this angle is equal to this one. So because you've got R here, you must also have R1 and R2. Can you see that? R1 and R2, because you can't say R, because R can, when you just say R could be this, R could be this. You see, so so you must say R1 and R2. So in these two triangles, in triangle OPR and triangle OQR, so what is happening? Angle R1 is equal to angle R2, which is equal to 90 degrees. Where did you get that from? You got that from because what? Because OR is perpendicular to PQ. To PQ. So OR, which is this, is perpendicular to PQ, which is this line. So because of that, this is 90, and this is also 90. Okay, remember in geometry, you don't just do things. Everything that you do, you must show where is it that it comes from. Okay, so R1 is equal to R2 is equal to 90 degrees. Why? Because OR is perpendicular to PQ. Okay, does that make sense? Okay, and then another important thing is that OP is equal to OI. Do you remember what I said earlier? I said if you have radii, which means radiuses, it does not matter where they are, but all of them are equal. So now I've got a radius here because it's from center to the circle, and then here it's also from center to the circle. Okay, so they are both radius. So because they are both radius, then it means they are equal. So OP is equal to OQ. What is the reason? It's radii. Which means in simple English, which means they are both radiuses. Okay, wonderful. And then lastly, they are sharing this line. Can you see? O R is what? Is common. Okay, so you've shown an angle and side and then a side, but this is not just any angle, it's a 90-degree angle. So from this and the above triangle, you can then see that what that triangle OPR is congruent to what? To triangle OQR. And then what is the reason? It is the right hand side. Okay, if you have forgotten how to do this, there is a video in this channel called Congruent Triangles. Go and look at that video so that you can recap how to deal with congruence, so that you can understand what is it that is happening here. All right, okay, so it turns out that this circle, if you can just flip it over, it can fit exactly to this one, or this one, if you can flip it over, it can fit exactly to this one. That means they are equal in length, in shape, they are also equal in size, so they are exactly the same, they are aligned to each other. Okay, now if that is the case, if these two triangles are exactly equal to the other, therefore if you take this one and put it over here, it means this will be exactly this. So therefore PR will be equal to what? Will be equal to RQ. Okay, now if this side is equal to this side, that means that this PQ chord is being bisected, because bisect simply means cut into two equal halves, and here we have already shown that this half is equal to this half. Okay, so that means that this line, the line that moves from here to here, and then which is perpendicular to this one, then it bisects what? It bisects PQ. So because of that, okay, you can then say OR bisects what? PQ. And ladies and gentlemen, this is what we are supposed to prove. This is our proof. This is how we show that our proof is done. All right. Okay. This is how you prove this theorem, Legendary personalities. So thank you very much for tuning in. This is our first theorem of grade 11, which is examinable both in grade 11 and in grade 12, which says a line drawn from center perpendicular to the chord bisect the chord. And then if you have used this theorem, you can show that you have used this theorem by simply writing this statement, which is a short version of this theorem, which is perpendicular from center bisect chord. Ladies and gentlemen, personalities, this is Mkondes Macaba from Tembela Maths Club, a club that helps learners to understand mathematics. Theorem number 2 will follow, but for now, let's call it what? Let's call it a day. But before we do that, remember, we've constructed here, we must also mention that from angle R, we then constructed angle, we didn't construct it basically, but we've named R1 and R2. From R, you produce R1 and R2. Okay, because we don't in maths, guys, we don't just rock up and things are there. No. Things should be explained where they come from. But ladies and gentlemen, thank you so much and have a lovely day and goodbye.